for number theory. So you can see I've given you a copy there of the 2014 paper. The 2016 paper, last year's paper, is also up there in Moodle. For some reason, the 2015 one isn't appearing, but I will put that up separately. It should automatically appear, but for some reason it's not appearing automatically. So I'll make sure that that goes up as well. So you'll have 3 past papers to work with. And we will be, they're not up there yet, but I will be putting up some work solutions to the last 2 2016 and 2015 papers. And then we'll start working through this from now. So I said, and I'll continue to say, like, if there's any particular topics you want me to say more about, or any particular tutorial questions in the book you want me to revisit the solutions of, feel free to suggest things like that. But I thought to get us started, we'd just start going through this paper and take up any questions that we encounter along the way, deal with any items that arise. Okay. So I hope you're all familiar with the structure of the exam. The structure of the exam you're going to face is the same, in that there are 2 sections, section A and B. There's 8 questions in total. There's a number theory section, section A, and a cryptography section, section B. This will focus. And you have to do, every question's worth 20 marks. You have to do 5 questions to get your 100 marks. But you must do, so that you're constrained, you have to do 2 number theory questions, 2 cryptography questions, and then your 5th question then can come from any of the remaining questions. So that way, you're as it should be, you have to deal with all the topics in the course. The questions roughly go through. The course from start to finish. So on the number theory side, the first question is about divisibility. But it is mixed up a bit. So we got some basic things about divisibility, something about prime numbers, and then an induction type proof in part D. Question 2 focuses on congruences, proving some basic things about those, the order Toshin function, and dealing with these large exponents. Question 3 from 2014. Ask you to prove, this is something we discussed, there's arbitrarily large gaps between the primes, meaning we want to find 2 prime numbers between which there's at least 1 million integers, none of which are prime. That can be found, and we can point to somewhere in the sequence of integers. We can point to a precise location in the sequence of integers where you're at the start of such a gap of at least 1 million integers between one prime and the next prime after. Then you're asked for that in question 3 part A. Question 3 part B is about the solution lifting when you're dealing with congruences modulo a prime power. And then finally, question 4 is a bit more on prime congruences. Linear congruence there in question 4. Chinese remainder theorem in question B. And kind of discussion, descriptive bit in part C about quadratic congruences, which leads us on to quadratic residues. And then the final part is to apply several properties of the Legendre symbol in order to decide whether or not that equation has a solution. It's a quick trip through the exam questions. Anybody unsure about anything about the structure of the exam? Okay. Then there's 4 cryptography questions in section B. But I'll leave John to discuss those of you who may already have done some work with the 2014 paper. So I thought we'd focus on question 1 to begin with. So basic things about divisibility, and some things about prime number here. So this is, I guess, mainly focusing on chapters 2 and 3. Just like a really quick look through what's in chapter 2. So we introduce, fundamental notion of the divisibility relation amongst the integers. This theorem, or at least certain parts of it, cropped up a lot here in 2.1, which goes through basic properties of divisibility. You really need to be kind of conversant or confident with using all of these. These are all used to prove various other follow-on properties of divisibility, and then properties of congruence, because congruence is defined in terms of divisibility and so on. And a key one we always came back to, we always seem to be referring back to, was divisibility of linear combinations. That if two numbers b and c were both divisible by a, then a automatically divides any integer linear combination of b and c. That one seems to just be used all over the place. Quite a fundamental property. But all the others are important as well. Transitivity of divisibility. If A divides B, B divides C, then A will in turn divide C. The kind of divisibility travels through B, if you like, so that A can divide C. Then we defined prime number, number 2, it only has itself and 1 as positive divisors. We considered the statement of the fundamental theorem of arithmetic, which says that every integer factors uniquely into product of primes, typically written like this, because each prime might appear to a certain power. Okay, so we have that unique representation for the integer n. We call that the canonical form. But the proof of that wasn't available to us immediately. We needed to build up a few bits and pieces to get to the proof of that. We introduced the notion of common divisors, so that's where you're looking at the relationship between two different integers in terms of looking at what factors they share, what kind of relationship two integers can have to each other. And this is measured by the greatest common divisor. This is this maximal common divisor of the two integers, A and B, and the greatest common divisor as well, it embodies all the common divisors. Okay? Because if D is the greatest common divisor of A and B, then any common divisor of A and B will in turn divide D. We also met this very important aspect of the greatest common divisor, which isn't by any means kind of obvious, I don't think. But the greatest common divisor between two integers D, it can be characterized like this, that it's the smallest positive integer that can be written as a integer linear combination of the two numbers A and B. That's a very useful fact to have about the greatest common divisor. Then chapter 2 finishes off with, of course, the Euclidean algorithm, which is extremely important. Is a very good, fast algorithm for finding the greatest common divisor of two numbers. That's kind of half the job it does. It obtains the greatest common divisor of two numbers, but it also, when you run through the sequence of integer divisions backwards, it gives you the linear combination of the two numbers equal to the greatest common divisor. It's the so-called Divisors identity. And then you got, a whole bunch of exercises at the end of chapter 2. And chapter 3 on primes kind of looks again at the definition of a prime number, and then very famous result everybody should know, which is the proof that there's an infinite number of primes, Euclid's proof. And then we go on to prove the fundamental theorem of arithmetic that we had glanced at in chapter 2. And then just started to look at more little bits and pieces about the aspects of primes, and then more exercises. And the next chapter was on congruences. So again, that's just a very quick look at chapters 1 and 2, which is the focus, which is the subjective question. So let's dive into these various parts. So I'll try and show you, how I would answer these exam questions, so to speak. Very often they can be answered in slightly different ways. But some general principles you need to keep in mind when answering these exam questions is, there is plenty of time. So it's a 3-hour exam, 5 questions. So the guideline is you've got, half an hour for each question, and then an extra half hour left over at the end, checking everything or spending longer in certain parts. So there is plenty of time. So what you should be seeking to do, as well as finding the answers to whatever the problems are, but always make sure you're supplying all the details that are asked for, and always look for opportunities where you can demonstrate your understanding of the course. That's the chief thing I'm looking for. So don't, I'd encourage you to put little explanation sentences and comments and justifications in where appropriate. Okay? So always be on the lookout for saying, have I given a good demonstration of my knowledge? But for some questions, some questions are short and sweet, like question 1 part A. There's only 3 marks going for it, so it's not going to require a lot. So it's asking for state precisely the definition of the divisibility relation A divides B on the integers. Okay? So with these definition type questions, you just want to make sure you really very clearly hit the nail on the head. Don't leave any room for ambiguity at all, and give something that is equivalent to the definition, something nice and precise. Okay, so given 2 integers A and B, and one thought I might have in the back of my head here is this going to work for every pair of integers A and B, or might there be some restriction that's needed? Does one of them have to be non-zero or something? I'll just keep that in mind. I'll continue writing out the definition, then I might just double check that. So given 2 integers A and B, we say A divides B, written as notation, A divides B. And generally with definitions, we tend to like to use this if and only if construction. This is the way of saying that, that what follows the if and only if is going to be exactly equivalent to this terminology. So if and only if there exists another integer, C, such that, now this is just make absolutely sure you get this bit the right way around. This is maybe a tendency, possibility you might mix things up and have it going in the wrong direction. But A is dividing B, so typically you think of A as being the smaller thing. So we can write the big thing B as the little thing A times another. So that seems pretty good. I've used if and only if, nice and precise. I've given the English first, I talked about the notation and how you read it, how you say it. And are there any, is this a valid definition for any pair of integers A and B? Yeah, I don't think there's no non-zeroness or anything to worry about here. Okay, so something like that would get you the full 3 marks. Although maybe even better would be just to give, say, maybe a couple of quick examples, a positive and a negative example. E.g., we could say 5 divides 10, since 10 is equal to 5 by 2. I mean, it's kind of trivial. I wouldn't really require these examples, I don't think, for full marks, but it fleshes out a definition if you give a quick positive and negative example. And we could say 3 does not divide 10 since 10 divided by 3, this quantity is not an integer. Genuine rational number, non-integer rational. Okay. Any questions about that? Yeah, question.
If you didn't put like B equals AC, did you just say that A is a multiple of B?
So given two integers, A divides B, written as that if and only if B is a multiple of A. Yeah, I mean, that's, if it was written out clearly and precisely, yeah, the only thing is you're kind of just substituting the word multiple for divisible then. It feels a little bit, I would maybe want to see the actual, you know, just to make it clear that it is the existence of another integer and that it's the product of those two is equal to B. I know that's exactly equivalent to saying it's a multiple of the other one. It just feels a little bit that, you know, if you're asked to define something, you know, here we're defining the term divides in terms of more basic stuff, kind of just pure arithmetic stuff. Whereas saying it's, you know, the one is a multiple of the other, you're kind of just substituting another term which is on the same kind of level as divides, you know, because then how would you define is a multiple of? Well, is a multiple of gets defined in the same way, doesn't it? Right? Normally, you know, you think of giving a definition as giving the conditions for the term in terms of kind of lower level concepts, if you like. It's a general guideline for, yeah, what you should define as definitions. You know? And then we define the, so later on, we define the congruence relation in terms of the divisibility. You know, once we already had divisibility defined, we could then define higher order kind of concepts in terms of that. Okay. Any other queries? So question B then is our first kind of proof type question. Use your definition from part A to prove that for all ABC, if A divides B and A divides C, then for all M and N and Z, A divides NB plus NC. So this is that very central, important property I was referring to a moment ago. This is the linear combinations property. Okay. Now, don't be intimidated by these proof type questions. You know, they are very approachable. They are things you should be practicing. And in the heat of an exam, you know, there are ways, you know, I don't normally say learn things off by heart. You know, that's somewhat of a dangerous approach, because when you try and learn proofs off by heart or memorize them, the danger is you misremember them or you get some of the details that are incorrect. So I think it's better off for something that reflects a more deeper understanding of the things, is that you get yourself into a way of working that you're able to recreate the proofs as necessary. Okay? So you're given a lot of information there, and there's a lot of structure that's already apparent there just in the question, and that can help you guide your proof. So first of all, you're given conditions. So it says in the question, for any A, B, and C in the integers, if A divides B and A divides C, then something follows, and you're asked to prove that, you're asked to prove the implication. So immediately your argument should start off by assuming the conditions. And these are all just taken from the question. So I'm going to let A, B, and C be three integers, and I'm going to let them satisfy those two divisibility statements. Okay, park them for the moment. Then at the bottom of the page, you might just do this, say, on a rough work at the back if you're just trying to reconstruct it. But you know I'm going to have to get to this conclusion that A divides NB plus NC. Where M and N are arbitrary pairs of integers. Okay? And if we can bridge that gap, then we've accomplished the proof. Okay? How are we going to bridge that gap? There's two ways to do it. You can either push the top bit down towards it, or you can pull the bottom bit up towards it. Okay? Now, we've got, facing us here on the page, we've got three divisibility statements. We've just gone to the trouble of giving a careful definition of what divisibility means. So again, almost without thinking, we can just write down the concept, exactly what you mean by these divisibility statements. So, i.e., if A is dividing B, it means there exists an integer, let's call it beta, and another one gamma, such that B is beta times A, and C is gamma times A. That's what it means for A to divide B and A to divide C. So we haven't really begun our kind of proof argument yet, because all I've done is put down the assumptions and just unravel the definition. In a similar way, you can unravel the definition of the conclusion. How is it that how can you get to a situation where you can claim that this statement is true? Only if you've set up the necessary facts that define that divisibility relation. And the necessary facts that define this divisibility relation here at the bottom is that the integer nb plus nc has to be expressed as something times a. So that's good. We've discovered a gap okay? If we can show that there's an integer in here, such that when you multiply it by a, you get nb plus nc, that's exactly the definition of a divides nb plus nc. And now this looks very, very doable. Again, all I've just been doing is just operating these general principles. But now look what we've got. We're trying to get to an equation involving b and c on the left and a on the right. It's a multiplication type equation. And what have we got up here? We've got two equations. One with b on the left, one with c on the left. And they both have a on the right, and they're certainly multiplication type equations. So it seems very promising that we can move from these down to this. Okay. Surely just some kind of little bit of substitution or something. Now this down here deals with these two integers m and n. Glance back at the question. So this statement down here is supposed to hold for every pair of integers, every pair of coefficients m and n. So I just say let m and n be z, two integers, no other restriction on them. Let me just go for it. Just try and form this mb plus nc. Use your assumptions. This is m beta a plus n gamma a, and of course, you can factorize that. Just basic arithmetic. So yeah, we have indeed filled this gap. So just stand back then, just read back through your argument, see if it works. See if it flows well, see if everything's explained, nothing's left ambiguous. So it says, let a, b, and c be three integers. Let them satisfy this, that a divides b and a divides c. Well, that means, according to the definition, that b is something times a, c is something times a. Bring in arbitrary pair of coefficients m and n. Form the required linear combination of b and c. Substitute in the assumptions. Do a bit of fiddling around with it to get what we need so we can claim the conclusion. Okay. So everything is justified there as either just basic arithmetic there in that manipulation in the middle, or the application of the definition of the divisibilities. So you could even put in little comments here by definition of divisibility. This is by definition of divisibility as well. That really hits the nail on the head, proves everything. Read the question again. Any queries about that? So like you might try and learn that kind of thing off by heart, but it's better to remember principles. Okay, certainly you need to know exactly what the definition of the divisibility relation is. Then just try and remember these principles for working towards proof. Put down the assumptions clearly, put down the conclusion clearly. Interpret any terminology that's in the assumptions and the conclusion. Here, it's just the divisibility relation. So interpret the divisibility relation here. Interpret the divisibility relation here. Okay, here we're assuming this divides this and this divides this. So we assume the existence of these other factors. Here we're trying to get to this point. So we interpret the definition backwards, but we don't, write in another integer there yet, because that's what we're trying to find. We're trying to prove that there exists this other integer. So that's the difference between assumptions and conclusions that you're trying to reach. And then having done that, you brought them very, very close to each other. Equation with B and C involving A on the right. Two separate equations involving B and C with A on the right. So surely you're just going to mush them together somehow. Yeah. Okay. And we look at the next one, part C. Part C. Okay, so this is another bookwork proof. Again, very, very central, important property. It's sometimes even people might say that this is equivalent to the definition of a prime number. So it's property of a prime number, but you could almost take this as a kind of roundabout definition of what a prime number is. Anyway, let's read it. So Euclid's lemma states that for every pair of integers a and b and p a prime, if p divides the product ab, then p divides a or p divides b. Prove this lemma. There's only 5 marks going here, and there's a bit of guidance here about the proof. It says use the concept of divisibility and greatest common divisor. Okay, so it's also assessing how well do you know what the greatest common divisor is, and also state carefully any results about these that you use. So that's a bit of guidance there that you don't necessarily have to prove everything from the ground up. It's kind of pointing you or pushing you towards relying on these concepts, divisibility and greatest common divisor, and you can quote any standard results about those that you want to use in turn to prove Euclid's lemma. Okay? So you don't have to prove those, just state them clearly. Just make it very clear that you know what those other results are and how you're applying them. And yet, this could almost be taken as the definition of a prime number. Prime numbers are those numbers p that satisfy this property, that whenever p divides a product, it always divides at least one of the factors, and that works for any pair of numbers, for any pair of integers ab. It's not as natural or nice as our definition of prime numbers, those with only 2 factors, themselves and 1. But it is equivalent. And this is the kind of central turning point that allows you to do the fundamental theorem of arithmetic as well. Quite important result. So let's go for it. Part C. So, just without thinking, write down the assumptions almost. So let A be the integers, and let P be a prime. And suppose that P divides AB. Almost without thinking, just kind of roll that forward a bit, i.e. there exists an integer x such that AB is equal to xb. Okay. Conclusion we're looking for is down the bottom. We might put it P divides A or P divides B. Okay, we're going from a divisibility statement involving P and AB to reaching a desired conclusion, which is an or, a disjunction, to use the logical terminology, but an or statement involving P divides A and P divides B. So it's not that surprising that there should be proof in this direction. There's maybe a little bit of a there's a neat approach. There's a very nice approach which we often use if you're trying to prove a final conclusion, which is in the form of an or statement. Trying to prove this directly, you can see it might be tricky because if if P, A, and B are general, I mean, you're not going to be able to prove that P must divide A. And you're not going to be able to prove that P must divide B, because it could be either conclusion. So that can kind of make it difficult. If you're trying to prove this just very simply, directly, it's hard to reach a firm conclusion, because the conclusion you're trying to reach isn't that P divides A, and it's not that P divides B, it's that one of them must be true. So how to approach this is, you may remember from your first year study of logic that the disjunction symbol, the logical or symbol, is equivalent to, and this happens with logical symbols, that all the set of common logical symbols and or not an implication, they aren't all independent symbols. Each one can be expressed as, if you like, the kind of logical linear combination of the other ones. And A or B is equivalent to, well, one way of writing it is not A implies B. If you think about it, this seems reasonable. I'm trying to reach a conclusion that P divides A or P divides B. Now, one way of making it a bit more definite, tight, is if I consider the special case that this one isn't true. If I assume that P does not divide A, well, that looks bad for proving this, because this is one of the parts of it. So if we assume that P does not divide A, the only way we're going to rescue this conclusion is if we can deduce here that this implies that somehow P must divide B. And of course, in the other situation where P does not divide A, if P does divide A, then straight away you get this conclusion. There's no more extra argument needed. If it was true that P divided A, then you can certainly say P divides A or P divides B. And you don't care whether P divides B or not, because you know P divides A, so therefore you can claim P divides A or P divides B. I can safely say I'm Irish or I'm the King of England, because I know the first bit is true. So I can tag on anything else into that statement. I can say I'm Irish or I shot Jay. I can say anything at all is going to be true. The disjunction of that is always going to be true if you know P divides A. So so this kind of shows you that a way to get into the proof, that there's only work to do. See, if P divides A, there's no more work to do. But if P does not divide A, that's the case where there's work to do. If P does not divide A, then we have to show that it must be the case that P divides B, and so to rescue this conclusion. But that makes it better for you, because it gives you extra information, an extra assumption to make, and a more definite conclusion, more simple conclusion to reach. Rather than trying to reach this fuzzy this or that conclusion, you get extra information, which is nice to use to build your argument, and you get a simpler conclusion to work towards, which is nice. We can home in on proving P divides B, rather than trying to home in on this, well, it could be this or it could be that. everybody appreciate that? Is there any more clarification on that?
If you don't know A or B, then like it could be either.
You could also run this whole thing as a proof technique by assuming P does not divide B, and then argue that P divides A. So, but yes, so I don't know. See, I'm dealing in a completely general argument. So, A is not any specific number. B, it's just standing for any integer. B is standing for any integer. But it is true that either P divides A or P does not. Either P divides A or P does not divide. If it's this, then there's no more work to do. Yeah, you agree with that? So it's only if it's this situation that there's a bit of extra work to do to rescue the conclusion. Yeah. Okay, so let's go for it. So we make this extra assumption. We assume P does not divide A, and just in brackets here, we just put a little comment to explain the rationale for that. If P does divide A, then the required conclusion is true. P divides A or P divides B. So that's this, if P divides A, you're finished. It's only if P does not divide A that you've got some extra work to do. Okay, so how does this argument go? We're talking about divisibility here. The thing we haven't talked about is the greatest common divisor. That's mentioned in the question as a bit of a guideline. Use that concept. Well, this comes in here. Because if P is a prime number that does not divide A, as P is prime, the only common divisor of P and A is 1. So that implies GCD of A and P is 1. So that's good. We've got our greatest common divisor concept in, as the question directed us. And then the question also, said use any related properties to these concepts as long as we clearly state them. And the natural thing related to, remember, we're trying to get that P divides B. Natural thing related to the greatest common divisor is Divisors identity. So this implies there exists a pair of integers m and n. Haven't used those yet. M and n, z, such that ma plus np equals 1. Okay, so we clearly stated that as a consequence of the greatest common divisor being. We're trying to reach this conclusion that P divides B. In other words, we need an equation which says B equals something times P. That is a bit foggy here, so there's no B here. We've got this equation. There's no B here yet. And we haven't used this assumption yet. We're going to have to use this assumption. That's another guidance in constructing your proofs. The questions that you're asked will not include red herrings or, you'll not be asked to prove something from something else unless the something else is important. So we haven't actually used this assumption in our proof yet, so we're going to want to use it somewhere. We've got this equation. We're trying to reach an equation that says B equals something times P. There's no B here, but there is a 1 here. So the fact that there's a 1 here means it's very easy to introduce the B. Simply multiply both sides by B. MAB plus NPB is B. Simply multiplication by B. And that's good because now you can see your AB, which we assume is a multiple of P. that doesn't need a justification, so it's on both sides by b. This is from above, from ab equals xp, substitution. And then just one extra line there. See, this can now be factorized. So this is mx plus nb, and p equals b. So we've got an equation that says b is some integer. This is certainly an integer. nb, but m and n and x and b are all integers. That's said here. X is an integer, m and n are integers, b is an integer. So this round bracket here is certainly an integer. So an integer times p is b, therefore p divides b. So assuming further that p does not divide a, that gets you to this conclusion that p divides b. So therefore, in summary, this means p must divide a or p divides b. It's entirely possible it divides them both. We know it must divide one of them. Okay. Again, a bit of a proof technique there for how to, and that you know is quite a common technique to see. You know, if you're trying to prove a disjunction, that's very common technique. It's really nice because it gives you an extra assumption and it simplifies the conclusion you're trying to reach. Any other questions? Ask about that. Okay, let's have a look at part D. So part D says prove that 2n plus 1 is prime, implies that n is prime. And there's a hint there, it says use the contrapositive of the statement. Okay, contrapositive of an implication is the implication in the other direction, but talking about the negatives of the negations of the statements. This is a different sentence, symbols in different order. It's a different logical sentence. It's equivalent to this. So this is true or false in exactly the situations that this is true. So they're logically equivalent. And this is another common logical proof technique used to, and it's just a way of rephrasing the result that you're trying to prove in order to make it more approachable, in order to give you more to hang on to. See, the problem with this is it's talking very negatively. 2n plus 1 is prime. That's kind of a negative type statement saying this number has no factors. And the conclusion you're trying to reach is kind of negative or empty. You're trying to prove that n has no factors. Yes, question? 2n minus 1. Of course, yes. That's prime. Thank you. 2n minus 1. But when you do the contrapositive, I know it's like, you know, you're trying to climb a tree, but it doesn't look climbable from this. So you walk around the back of it, there's different branches, more things to get a hold of. You're still climbing the same tree, but in a different way. That's what this is like. So the contrapositive is n is composite. That's the negation of n is prime, implies 2 to the n minus 1 is composite. So this is good. You've walked around the tree. Suddenly there's loads of low branches, things to hold on to. This looks much more approachable, okay? Because you can immediately unravel this assumption. N is composite means there exists non-trivial factors that multiply together to give n. So you get ammunition to use. And the conclusion you're trying to reach is also more reachable now. So let n be composite, i.e. n is equal to an r times s, where both r and s are non-trivial. They're both strictly bigger than 1. And the conclusion you're trying to reach, 2 to the n minus 1 is composite. That's reachable. It's clear how you reach it. You just got to show that there's a factorization of 2 to the n minus 1 into non-trivial bits. You don't want to prove it's got a factorization that could somehow be 1 times 2 to the n minus 1. Prove it's composite, but genuine factorization. So where does it come from? Well, 2 to the n minus 1 is equal to 2 to the rs minus 1. But then this can be seen as a difference of powers of s. Difference of s powers. So this is 2 to the r to the s minus 1 to the s. And difference of powers like that always has the plane difference as a factor. So 2 to the r minus 1 will be a factor of that. And you'll have 2 to the r into s minus 1 plus 2 to the r into s minus 2, all the way down to the last one, the 2 to the r and then plus 1. You multiply those out. In fact, you got 2 to the r here and minus 1 here. Means that when you multiply these two brackets out, all the cross terms cancel except for this term times the product of the two leading terms and the product of the two trailing terms. So you get back immediately 2 to the rs minus 1. And that means 2 to the r is composite, since you just have to say that 2 to the r minus 1 is strictly bigger than 1. And that's true because r is strictly bigger than 1. So this is at least 4 minus, this is at least 3, this factor. And this factor over here is certainly strictly bigger than 1 because s is strictly bigger than 1. So there's at least, s is strictly bigger than 1, it means s is at least 2. So this bracket at least begins at 2 to the r. So it might just consist of these two terms, if s is the smallest it can be. If s is just equal to 2. Because the first term is 2 to the r, s minus 1. So the first term would be 2 to the r. So the fact that both r and s are non-trivial means that these two factors, you can say they're non-trivial. This other bracket is bigger than 1, since r is bigger than 1 and s is bigger. So you've got this non-trivial factorization, so you can claim that 2 to the n minus 1 is constant. This was 7 marks in total going for that, so yeah, would want to see some kind of justification for the non-triviality of those items. Okay, better leave it there for this morning. So we'll continue doing stuff like this